Welcome to this deep dive. Today we're looking at some really interesting research. The paper's called Sleep Time Compute, Beyond Inference Scaling at Test Time.
That's right.
And for anyone, getting into AI, especially LLMs, the deal making these models think hard when you ask a question, that test time compute, it can be slow and expensive.
Yeah, definitely. It's a trade-off, isn't it?
So this paper seems to offer a different path, maybe something useful for AI learners listening in.
Exactly. I mean, the core problem they're tackling is pretty fundamental. We know giving models more compute power when they're answering usually makes them better on tricky stuff.
Like giving a student extra time or resources during a test.
Right. But that extra thinking time, it adds up. Latency goes up, costs go up.
Okay, so let's unpack this sleep time compute idea they're pushing, it sounds like. Instead of just working when asked, the model does some prep work offline.
That's the gist of it. While it's idle, maybe between queries, it looks at the context it already has, like a document or code or chat history.
Stuff it already knows.
Exactly. And it tries to anticipate, what kinds of questions might come up. It pre-calculates useful stuff.
So like our student analogy, again, reviewing notes, maybe doing practice problems before the exam even starts?
Precisely. And the big claim here is that this sleep time work can seriously cut down the computation needed at test time for the same accuracy.
Wait, cut down compute and maintain accuracy?
Yeah, and they even suggest it might boost accuracy in some cases.
Okay, interesting. So our mission today is really to get under the hood of this idea. How does it work? How did they test it? And why should someone learning AI care?
That's the plan. Understand the concept, the experiments, and the potential impact.
It feels like it could be a pretty big shift in how we think about using these models. So yeah, let's dive in. Where do we start? Maybe the standard way things work now.
Good idea. So normally the test time compute model is simple. You give the LLM a query and any context it needs all at once.
Right. Here's the question. Here's the background. Go figure it out.
Exactly. It processes both together and spits out an answer. Like that student getting the question and all the info right then and there. Got to solve it on the spot.
Okay, standard stuff. But the paper argues that's not always how real AI applications work, right? They talk about stateful applications.
Yes, exactly. Many apps have context that sticks around. Think about asking questions about a long PDF you've uploaded.
The PDF is the context, and it's there before I even type my question.
Precisely. Or a coding assistant. The whole project's code base is the context. Or even chatbots that remember your earlier conversation.
Right. The context persists. It's not just a one-shot thing.
And that's the key insight. In these stateful scenarios, the context is available before the query. So while the model is idle, waiting for you, that's the sleep time.
Okay.
And during that time, it can actively process that existing context. It's not just sitting there. It's making inferences, maybe summarizing key points, creating a re-represented context.
So it's like building a better set of notes, maybe, anticipating what might be important later?
That's a great way to put it. It's proactive preparation based on the available info.
Okay, so our student isn't just waiting passively. They're actively reviewing, maybe predicting potential questions based on the material they have.
Perfect analogy. Then, when you finally ask your question at test time, the model doesn't start from scratch with the raw context. It uses this pre-processed, re-represented version alongside your query.
And because it's already done some groundwork,
it hopefully needs much less computation at that moment to get you the answer. Less latency, less cost.
Okay, the concept makes sense. How did they actually test this? What kind of data did they use?
They needed to simulate these stateful situations. They took existing math reasoning data sets. You mentioned GSM-Symbolic and AIME.
Yeah, standard benchmarks for math problems. Some basics, some pretty tough, right?
Elementary word problems up to advanced high school competition math. And they adapted them. They created stateful versions.
How'd they do that? How do you make a math problem stateful?
It was pretty clever, actually. They basically split each problem. Part of the text describing the setup became the context.
Like the background information in a word problem.
Exactly. And the final sentence, actually asking for the answer, became the question. So the model would see the context first during sleep time and then get the question later at test time.
Ah, I see. Simulating that delay.
Yeah. They use different versions like GSM-Symbolic P1 and P2 with thousands of examples, increasing difficulty, and also AIME problems from recent years.
Got it. So the model gets the setup, thinks about it, then gets the actual question.
That's the core setup. But they went further. They wanted to see how this worked if you ask multiple questions about the same context.
Like in a real conversation, maybe digging into a topic.
Right. So they created another data set, multi-query GSM-Symbolic. They took the stateful problems and used another AI, O3 Mini, I think.
Using AI to generate test data for AI data.
Huh. Yeah, a bit. They prompted it to generate extra follow-up questions based on the original context. Like, if the context set up a scenario about apples and oranges, it might generate questions about the total fruit, the difference, the cost, etc.
Okay, so one setup, multiple related questions.
Exactly. The idea was to test amortization. Can the cost of that initial sleep time compute be spread out effectively if it helps answer multiple later questions?
That seems really relevant for chatbots or Q&A systems. You do the heavy lifting once on the document, then answer lots of questions about it.
That's the hypothesis. Like, studying a chapter really well means you can answer lots of different questions on it more easily.
Makes sense. Did they look at anything beyond math problems?
They did. They also use a benchmark called Celebi features, which is from software engineering. It involves GitHub pull requests where code changes across multiple files.
Okay, more like an AI agent task, where the code base is the context.
Exactly. Seeing if sleep time compute helps in these more complex agent-like scenarios where the context is large and the tasks involve understanding code relationships.
All right, so they had these different ways to test stateful interactions. What did they actually find? Did the sleep time thing work?
One of the headline findings was what they call a Pareto improvement. Basically, think of that trade-off. More test time compute usually means better accuracy, but also higher cost latency.
Right, you usually have to pick a point on that curve.
Well, they found sleep time compute effectively shifted that whole curve.
Shifted how? Better.
Yeah, better. It meant they could achieve the same accuracy as the standard approach, but with way less compute at test time.
Well, much less.
The paper suggests around a 5x reduction for the same accuracy on those stateful math data sets.
Wow, okay, 5 times less compute for the same answer quality. That's really significant.
It really is. Think about the cost savings, the speed improvements. That's a big deal for anyone deploying these models.
Absolutely. Did they try pushing the sleep time compute harder, like more offline thinking?
They did. They experimented with things like generating multiple different re-represented contexts in parallel during sleep time, or just letting the model think harder offline.
And what happened? Did more sleep time work always mean better results?
It led to further improvements, yeah. They saw even higher accuracy by doing more work during sleep time. The numbers were up to like 13% better on GSM-Symbolic and 18% on AIME in terms of peak accuracy.
So not only cheaper for the same accuracy, but potentially more accurate if you invest more in the sleep time phase.
Exactly. But there was a catch.
Always a catch.
Well, they did notice diminishing returns. Especially with generating lots of parallel representations during sleep time, it seemed like after a certain point, it didn't help much more, or maybe even confuse things.
Okay, so there's a sweet spot. You can't just let it run forever offline and expect miracles. Makes sense.
Practical limits.
Well, what about that multi-query idea? Did the amortization pan out? Was it cheaper per question?
Yes, that was another key finding. On the multi-query dataset, they showed that the benefit of sleep time compute really stacked up when you asked multiple questions about the same context.
So the upfront cost paid off over time.
Definitely. They found the average cost per query dropped significantly, up to maybe 2.5 times cheaper when there were around 10 questions per context.
That's a big economic argument for applications with ongoing interactions, like a help desk bot or a research assistant.
Absolutely. It makes the whole approach much more cost-effective in those scenarios.
Did they find out when sleep time compute works best? Like, are there certain conditions?
You looked into that, yeah. They analyzed how predictable the question was, given the context.
Predictable? How do you measure that?
They used another model, Llama 270B, to estimate the probability of a specific question arising from a given context. High probability meant predictable.
Okay, so if the question was kind of obvious given the setup.
Then sleep time compute gave the biggest benefits. The more predictable the upcoming query, the more effective the offline preparation was.
That makes intuitive sense. If you can anticipate what's coming, prepping for it is more valuable.
Exactly. If the question is totally out of left field, the pre-computation might not have helped as much. They included some examples in the paper showing predictable versus unpredictable questions.
Right. What about the software engineering test, the SWE features? How did it fare there?
That showed a slightly more nuanced picture. At lower test time compute budgets, so when you wanted a quick answer, sleep time compute helped improve performance. The F1 score, their metric, went up.
So good for faster, maybe less complex coding tasks?
Potentially, yeah.
Yeah.
But they also found that if you were willing to throw a lot of compute power at the problem during test time, sometimes the standard approach, without sleep time, could eventually catch up or even outperform it slightly.
Interesting. So for really complex, maybe non-obvious coding problems, just giving the model maximum power at the time might still be the best bet, even if it's slower.
That seems to be the suggestion from that specific test. It highlights that the benefits might depend on the task complexity and your compute budget at test time.
Okay, so let's get into the how. How did they actually implement this? You mentioned function calling.
Yeah, that was the mechanism.
Yeah.
They basically gave the model new tools, new functions it could call during its operation.
Like special commands.
Sort of. Two main ones. Rethink memory and finish rethinking. During sleep time, the model could call rethink memory.
And what did that do?
It told the model, okay, look at the context you have now, process it, and generate a new, maybe better representation of it.
Like refining its notes.
Exactly. And it could do this multiple times, up to 10 times in their experiments, calling rethink memory again and again on its latest understanding.
So an iterative refinement process during downtime.
Precisely. And when it decided it was done with its offline thinking, it would call finish rethinking.
Signaling, okay, I'm prepped now.
Yep. And the paper has some conceptual code examples showing how this flow works. They also showed the actual prompt they used for the AIME problems during sleep time.
What did the prompt say?
It basically instructed the model to take the context, make deductions, try to figure out intermediate steps, and anticipate where the problem might be going, essentially getting it ready for the final question.
So explicitly telling it to pre-process and anticipate. How does this whole sleep time idea compare to other ways people try to make LLMs faster or better, like just throwing more compute at them during test time?
Well, the paper contrasts it with those existing methods like sequential scaling, just thinking longer, or parallel scaling, exploring multiple paths at once.
And the difference is?
Sleep time compute is orthogonal, really. It's not just about more compute at test time. It's about shifting when some of that compute happens, leveraging that idle time before the query even exists.
Okay. What about things like speculative decoding? That's also about speed, right?
Yeah, speculative decoding aims to reduce latency too, by sort of guessing the next few words the model will generate, but the goal is different. Sleep time compute isn't just generating output faster. The information it produces during sleep time is used as input for the later reasoning process at test time, aiming to make that reasoning more efficient and potentially more accurate. It's about smarter preparation, not just faster generation.
Got it. Pre-computation for better reasoning.
Exactly. And they relate it to classic computer science ideas like caching or prefetching data. It's that same trade-off. Do work up front when things are quiet to make things faster when they're busy.
Okay, pulling it all together then. Why is this research important for someone, say, studying AI or thinking about building AI apps? What's the big takeaway?
Well, the potential upsides are pretty compelling, aren't they? Reduced latency means faster responses for users.
Which everyone wants.
Lower inference costs make deploying powerful AI more feasible, maybe even on smaller devices eventually.
More accessible AI.
And then there's the accuracy boost in some cases. It's not just cheaper, it might actually be better sometimes. That combination is really attractive.
And it seems especially relevant for those stateful applications we talked about.
Definitely. Coding assistance, document Q&A, long-running chatbots, personalized learning tools. Anywhere the AI interacts with the same context over time, this approach could really shine.
And that finding about predictability is interesting too. It suggests you could be strategic about where you apply sleep time compute.
Right. If you have a system where you can somewhat anticipate the user's next steps or likely questions, that's where you might get the biggest bang for your buck with this pre-computation.
So summing up this deep dive, sleep time compute looks like a genuinely promising way to optimize LLMs. It shifts compute offline, potentially giving us faster, cheaper, and sometimes even more accurate AI, especially for stateful tasks and related queries.
Yeah, and I think the really surprising thing is that pre-computation isn't just a cost-saving trick. It can actually enhance the quality of the result. It kind of challenges the simple idea that all the thinking has to happen right when the question is asked.
It really does. It makes you wonder, how could this idea change how we design AI systems in the future? If models can proactively prepare, what does that enable?
Imagine assistants that anticipate your needs based on your calendar or current project, prepping information before you even ask. It opens up a lot of possibilities beyond just faster Q&A.
Definitely food for thought, a different way of interacting with AI, perhaps.
For sure. And for anyone listening who wants to really dig into the mechanics, the researchers made their code and data available. The link's in the paper's abstract, so you can actually play around with it.
Great pointer for the hands-on learners out there. Well, this has been a fascinating look at sleep time compute. Thanks for bringing this paper to the table.
My pleasure. It's definitely an area to watch.